My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 521. In this lecture, I will continue my discussion on gradient descent algorithm and its geometric intuition. Gradient descent algorithm itself works like this. Let me assume this is my x, this is, let me say this is my x and this is my y equal to f of x. What is step 1 in this particular algorithm? Step 1 is pick an initial point x naught at random. Pick any point, it could be any point on x axis. This is step number 1. What is step number 2? We want to find x1 such that x1 is closer to x star. What is my x star here? Let me say this is x star, optimal value of x. Yes, I will repeat. We want to find x1 such that x1 is closer to x star, the optimal value of x, then your x1 must be closer to x star than x naught. So you want to pick your x1 somewhere in the region between, you have to pick x1 somewhere in the region between x star and x naught. How do you pick? It is a very simple rule of gradient descent algorithm, that is x1 equal to, what is this? This is x1 equal to, this rule is important, x1 equal to x0 minus r into df by dx at x naught. Your step size is, let me assume, this is, so what does it do? Let's see. This r is constant, r is step size, r is often called as step size. This is a constant that you will fix. We will see what happens as step size changes. For right now, for simplicity, let's say this is this step size is constant. Let's assume, let's take my step size is equal to 1, isn't it? How to pick the right step size? It is a very interesting area of research. Let's assume your step size is 1. Now what is df by dx at x naught? That is important. Yes, df by dx at x naught. What is df by dx at x naught? Is nothing but slope of this line. This df by dx at x naught, it is slope of this line. You have to find slope of this line. Now what is the slope of this line? Slope of this line is positive. That is important. What is the slope? Slope is positive, isn't it? Now what is my x1? x1 equal to x0 minus, what is my r value? My r value, we are assumed 1. df by dx at x naught is positive, which means you are subtracting something from x naught. From x naught you are subtracting, subtracting something from x naught. You are subtracting positive value from x naught. That's important. You are subtracting, here you have some positive value, you are subtracting positive value from x naught. When you do that, what happens? You have to move towards x star. You have to move towards x star. What does it mean? You are subtracting positive value from x naught, means obviously x1 is less than x naught, because this is positive. Why it is why x1 is less than x naught? Why? What is the reason? This is positive, isn't it? Because this particular quantity is positive. You are subtracting positive quantity from x naught. Therefore I can say x1 less than x naught. x1 is somewhere in between x star and somewhere in between x star and x naught. Notice that because your slope or your derivative at point x naught, just observe, your derivative or slope at x naught is positive, and you subtracted this with step size 1. You are moving closer to x star. That is important. You are moving close to x star. Your x1 is closer to x star than x naught. Now let's see the other way around. Let's imagine what would have happened if my x naught is on the other side. Let me assume now my x naught is this side. let me say it's other side, isn't it? Let's assume my initial point, this is my initial point. My initial point is here. Let's assume my initial point is here, isn't it? And this is and this is I can say this is x star. What is this? This is x star, isn't it? Now, what is our update? Our update is x1 equal to x0 minus r into df by dx at x0. Your x1 is somewhere in this region. Your x1 must be somewhere here. Your x1 must be here, isn't it? x1 is somewhere in this region. Our df by dx at x0 is negative. At x0, what is your df by dx? df by dx is negative, negative value. I already discussed this one. df by dx is negative value, and we said r equal to 1, we assumed r equal to 1. So what happens to my x1? My x1 equal to x0 minus 1 into df by dx. As we are discussing, df by dx is a negative, therefore this is negative. Therefore what happens, which implies x1 is greater than x0, which means x1 is closer to x is closer to x star than x0, whether you pick the initial point on left side of the minimum or right side of the minimum, it doesn't matter. This update function works. In our second step, basically we got x1. Since we got our x1, let's draw the function again. Let me go back and continue my discussion. Our third step is here. Let me, anyway, we calculated this. Now what is my x2 equal to x1 minus r into df by dx at x1, isn't it? Again, slope here is positive. Yes, what is the slope here? Here slope is positive, isn't it? At which point? At x1, at point here slope is positive, isn't it? x2 is somewhere still, it's still close. x2 this x1 is closer to x star. x2 is somewhere, it's still closer, isn't it? This is second iteration. Similarly, at any iteration, what we do is xi plus 1 equal to xi minus r into df by dx at xi. This is the update, isn't it? This is simple iterative algorithm. Using this, we will get, we start with x0, randomly and go to x1, x2, x3, so on, xk. Let's assume at some iteration k, we reached xk equal to xk minus 1 minus r into df by dx at xk minus 1. Once we reach xk, let's assume we computed xk plus 1. If xk plus 1 minus xk is very small, which means your xk is reached very close to x star, then it's very small, then I can say, then terminate your loop and declare x star equal to xk, because you are updating from x0 to x1 to x2, so on, xk to xk plus 1. If the difference between xk and xk plus 1 is very small, then I can say x star equal to xk. In such case, xk is optimal value. This is how gradient descent works. Gradient descent is an iterative algorithm with simple update function xi plus 1 equal to xi minus r into df by dx at xi. This is update function. Remember, if you have a vector, if you have a vector function, this df by dx is simply replaced by del f with respect to x at xi. Whatever your df by dx, you can replace it with del f with respect to x at xi. Now, here one very interesting aspect that I want to cover. Let's draw this function. Again. Let's assume this is my x star. You know what is x star? This is my minimum. This one, which one? This is my x star. It's a minimum value. At any iteration, xi equal to xi minus 1 or minus r into df by dx at xi minus 1. Remember, as we are coming closer and closer to x star, my slope is also reduces, and eventually our slope becomes 0. So at every iteration, our slope is decreasing, which means df by dx at x naught is greater than or equal to df by dx at x1 is greater than or equal to df by dx at x2, so on. So remember what is happening. Slope or the gradient is slowly reducing. What happens in gradient descent? Initially from x0 to x1, we will make a big jump from x0 to x1, because this gradient df by dx is more. Initially df by dx is more. You come closer and closer to your solution, you will make smaller and smaller jump. So on x-axis, if you want to look at it as df by dx at x naught is significantly at x naught is significantly more than df by dx at x1, we will make a big jump from x0 to x1. Our r is kept almost constant. Let's assume r is constant, and which is equal to 1. Then after making big jump smaller, we will make small jump smaller and still smaller as we move from x0 to xk, x0, x1, x2, so on xk. Our move will decrease slowly. Just try to understand this lecture carefully, so that in my next lecture, that is in lecture number 522, we will try to understand learning rate or step size. Thank you very much.